Okay, everybody. Yeah, this is we're getting down to the end here. This is the penultimate meeting of for the class. So we have a meeting next week. Then I think that's it. So this is week 5. So before we jump into anything or everything, I mean, really the primary opportunity here is for you guys to ask questions that you may have run into as you were going through the studying. So anybody have any questions you want to throw out there? Don't be shy.
Jay, when it comes to using a charge controller, do you set the charge controller for its depth of discharge to allow in the battery?
Yes. Yes, typically, unless you're buying a cheap one, like if you're making a little solar generator or whatever, some of those charge controllers that are 14, 15 bucks, they just come preset and that's all there is. But most of the like whole home charge controller types, they're going to be either programmed within the unit itself or programmed within the inverter. So in the inverter, there's a menu system typically, and you can go in and say, I want to go to a 50% depth of discharge or a 90% depth of discharge or whatever. So that's going to happen within the inverter in most cases for a standalone system.
Thanks.
Uh-huh. Yep. Any other questions? I know there was I did get a question, speaking of charge controllers, about the difference between a battery management system and a charge controller. And there's, with lithium ion batteries, typically the battery bank comes with a battery management system attached to it. So that's something that is necessary for the lithium ion battery to work properly. That's different than a lead acid battery where you can just sort of buy the battery. And it deals with cell maintenance and avoids overcharging and things of that nature. Well, that's not exactly the same as a charge controller. So when you go and buy a battery bank, there's going to be an electronic battery management device integrated into that. There may also be a charge controller integrated, but that's probably not the case. That will probably be integrated in with the inverter. So more and more of these kind of systems, and this is more for a grid interactive, like a DC coupled or an AC coupled system. Those are typically becoming more and more proprietary, where all the bits are from the same manufacturer, and the charge controlling mechanism will be integrated into the inverter or perhaps into the smart switch if it's got that. Or maybe even into the battery bank, but you'll not typically buy a separate unit as a charge controller. It will be part of the system. But if you're making a small standalone system and using lithium ion batteries, then you will need to buy a charge controller that is tailored towards lithium ion batteries. So, all right, any other questions here? Trying to remember some that came up during the week. Let me jump into my emails to prompt me. Is anybody having any problems with the equations, with the math? That's oftentimes. Yep. Somebody have. Did you say you did, or was that background noise? Right. Oh, one question that came up occasionally there is, in some of those problems, we have D rates. So some of the problems will say, okay, figure this out. The D rate is 75% or the D rate is 90%. And the question has been, where did those D rates come from? How were they calculated? And most of them in the book, I just simply pull out of thin air. Unless it's a problem where you're supposed to figure out what the D rate is, I've just tried to throw in a D rate value that is typical of a system. But when we talk about D rating, no system is going to be 100% efficient. So the D rate is really a factor of a lot of things, but it's a factor of what product you're actually installing. In today's world, a D rate of around 90% is not bad as just kind of a typical thing, where you're going to have a certain number of percentages lost in the DC to AC conversion in the inverter. That's going to be in the range of 2 to 3% anymore. There's going to be some loss due to voltage drop. Remember, we try and minimize voltage drop to less than 2%. So that's going to be there. And so now we're up to 5%. There's going to be some loss due to connections, connectivity, shading, dust, things of that nature. If you've got string inverters, there's going to be additional losses due to panel mismatch, because the lowest common denominator is going to dominate the string. So if it's a plus or minus 5%, it's going to be minus 5%. But when we have module level power electronics on each of the panels, then you're really looking at that evens out. So that's not in there. So when I do microinverter evaluations because of the individual module or no string issues, I usually am in the 8 to 9% D rate range. If you've got a string inverter, it might be 15%. When you've got batteries, that's going to add another 10% or 15% for battery internal losses. So now that's with lead acid batteries. With lithium ion, I'd throw in 5%. So all of this is sort of just how do you figure out the inefficiencies of the system? And if you're doing the number of these, you'll get a sense of it. I always caution that if you're doing this professionally, sort of under promise and over deliver. So that's a good place where you can increase your D rate. You're going to say, okay, this system's not going to produce as much as I think it really will. And if it produces more, great. Then you come off as a great installer and your customer's happy. But if you overpromise, then they're going to say you did a bad job. So that's just something to consider when you're out there designing these things. All right. Let me see if and again, if you've got a question as I'm talking here, just feel free to jump in and interrupt. I know that I had actually more than what I'm probably going to be able to get to as far as requests to do some of the designs. So I'm trying to see which one is, there we go. Okay, so I'm showing, I think this is your bill, Fahim, is that right?
Yes, it's under my wife's name. So
Okay, all right. So it's your identity, right? Your nom de plume, right?
yes.
Okay. So this is a typical electric bill here. So one of the things that you're going to do when you first assess a project is the first thing you're going to do is get a copy of the electric bill. This would be a typical load assessment for a grid connected system. And when we look through this electric bill, usually these electric bills are going to give us the last year's worth of usage. We're not going to care too much here about natural gas, but if we start looking at the monthly averages, let's see, current month, time period, do they do annualized averages here? Just trying to see them.
I think I put it in the email. I just added them all up, and I think it's 11,505 kilowatt hours for the whole year.
11,505 kilowatt hours for the annualized.
For
okay.
Annualized, yes.
Okay, so do you mind if we jump in and show where this house is? I mean, I've already shared your address, so they're coming after you anyway. So that's Wildwood Lane. I'm writing some of this stuff down. Mahomet, Illinois. All right, so the next thing that we would do is, I think I have to actually stop sharing each time. And then we go into our All right, so we go in and we're going to look at, let's say PV watts. So I had you down as 1312 Wildwood. Is that right? Mamet. All right. Does that look like where you are? Just outside of Champaign?
Yes.
Yep. Okay. So now well, actually, I need to jump into PV Sketch here to see what kind of orientation, where we would put this on your home. Now you could use any type software for this, but I just use this one because it's cheap and it does what I need. There you are. So this will show your house. Does that look about right?
Yes.
Okay. So looking at your home here, you've got a lot of trees. So clearly the only location south is to the bottom of this screen, but it looks like either on the front roof here, just in this location, but you've got some shading issues from this tree in front.
Yes.
Or
I'll have to cut down the
in the
tree.
back. Okay, if you're going to cut down the tree, life is good from a solar perspective, maybe not good from a marital perspective. We'll have to see. But and do you have any restrictions in your neighborhood about having solar on the front of the house towards the street?
No, we don't have any
Okay.
restrictions for that.
All right. So it's showing me, I'm going to go ahead and just kind of roughly mark in, assuming that tree's gone, the profile of that part of the roof. And going to move all the pictures of you guys away from there. And I need to get my orientation correct. So that's is that 172? Yeah, maybe 173. What I'm trying to do is get the arrow pointing in the right direction here. So it looks like it's about an azimuth of about 170.
Okay.
Now we would have to go and do an assessment, but I'm going to assume the roof slope is about 20-degree pitch. That's fairly typical.
Yep.
And
I just have one comment about the area, and
Okay.
that is you have selected two roofs. One is, so our house is 2-story.
oh,
So part of it is actually the garage roof.
so and it's on a different level.
It is on a different level. So
Okay.
by the chimney, yep, that's the chimney.
All right. So let's go ahead and reduce the size we're dealing with. We can put in a second array down here if we have to. But yeah, okay. So, all right. So I've selected this. It's telling me it's about 50 feet by about 17 and a half feet is the area that I've got to work with. Now, if we zoom in on it, I might be able to see it's kind of some of the resolution isn't there, but are there any vents or chimneys or things? That looks like a chimney right there to the right, right?
Yes, and there are no obstructions. It's all on the north side roof.
Okay.
The vents and everything. So this
All
is
right, so
pretty nice surface.
then I'm just going to go ahead, since we're here, I'm going to throw in just randomly. If I were doing this for real, I'd pick a real solar panel and I'm going to assume these are going to be portrait, and I'm going to just make an assumption. I'm going to use end phase. And I'm only going to I'll put in a 10% D rate here, and then I'm going to ask it to go ahead and generate the design. And what I'm getting here, and here's where I have to make a few changes clearly, because my orientation isn't exactly right. I've got them cockeyed a little bit. So let's try 73 degrees. Redesign that, see if looks like I made it worse. Yep. So let's try 167. There we go. Now I'm looking better. Yeah, I did just a little too much there. So it looks like it's 168 azimuth. And at this point, yeah, so you're at 168. And for me to get the amount of setback and everything, I may have to modify this a little bit. But I'm going to, now that I've moved everybody, it's telling me that I can pretty much think that I could get about a 13 kW system onto the roof. So that's really what I'm trying to figure out just right here. Now I'm going to jump back over into my PV watts. Did it reorient you here into PV watts now? Am I still on the right screen?
Yes.
Okay. All right. So if I plug in a 13 kW array, I said my system losses were 10% tilt degree, and we said it was about a 168. So 168 azimuth. And now I can just sort of find out how much will this generate. Well, you said you need 11,500 kilowatt hours per year. What this is telling me is this system, if I went to the full amount that I can put on there, is going to generate somewhere around 18,000. So more than enough. I'm at about 40 or 50% too much. You get 4.71 hours of insulation there. So I could actually reduce this down. You can play with this. If I say 8 kW, and now we're into the right range. So an 8 kW system is probably going to do you just fine, get you right at 100% of your energy. So the information now that we know is we need an 8 kW system, and the orientation of your house is 168. I could maybe avoid getting rid of that tree. If I remove those, that's 11 kW. I can still keep stealing panels. It's down to 10. That's 9. Yeah. So there's your 8 kW system right there. So, you will probably get a little bit of shading issues from these trees, but not as much as you might think. So we could factor that into the D rate. So now you've got an 8 kW system, about 24 modules. So you could go to some wholesale distributors, start pricing these things out. But a rough estimate anymore is around $3 to $3.30 a kilowatt hour. That's fully retail, full retail. So if we take 8,000 times 330, say, that's going to be what? 8 times 3 is going to be 24, and 26 or $27,000 retail to install that system, if you went out and hired somebody to do it. Now, of that number, of that 26,000, say, about 13,000 are soft costs. So you could expect, if you do this yourself, realistically to have in the neighborhood of $13,000 in cost. Assuming because after taking this class, you're going to be a whiz at all of this. And so you could go out and install it for in the neighborhood of 13,000, 14,000, depending on permits, things like that. All right. So I'm going to stop sharing that. I'm not going to go into the full analysis, but that's going to give us a pretty good idea of the system. So if I wanted to try and put together a one-line drawing, I could go ahead and get here to my, I need to figure out how to get to another. There we go. All right, so at this point now I would start designing it where I've got, okay, the rooftop array, we know that's an 8 kW system here. Are you thinking you want to do, well, let's just assume you do a SolarEdge DC coupled system.
Yeah, that's what would be interesting.
Okay, so what we would end up doing is looking at the solar panel that you suggest or that you're going to use. And let's assume that the, actually with SolarEdge, I think I have to go and find the output amperage and voltage of those strings. And it seems to me that each of those strings, well, let's just look it up. How do I get out of screen sharing? There we go. Stop sharing. I'm going to have to go into another screen here. You guys are really testing my ability to use this technology. All right. So if we look at SolarEdge strings, and let's see, is this going to give me? So let's say we're using the optimizer, this particular optimizer here. Each optimizer has a little bit different specs. So this one doesn't have the spec sheet with it, does it? So this is the SolarEdge 370. Trying to find where there's the data sheet maybe. Hopefully that's going to tell us everything we need. Wait. What I'm looking for specifically is how many panels in a string and what is the output amperage. So this is taking me into something that's not SolarEdge, didn't it? All right. Let's see. Maximum 370. Lots of looking up of stuff.
Would that be the data sheet? Or...
Yeah, it might be the data sheet or it might be the installation sheet. I know I clicked on. Here we go. Yep. So we're looking in this middle column, the 370s. It's telling me it's 98.8% efficient, maximum output. What is the output current? 15. So 15 amps. And how many in a string? Single phase maximum is 25. And the minimum is 8. Right? So it looks like we can do it with just one string, right? Because we said how many panels were in your string?
12?
24 modules. So we could go with one string.
Okay.
All right. So if I get out of here, we're just right up to just the one string, which is quite good actually. So let me jump into the whiteboard. And so what I'm saying now is there's one string, and what it does is it modifies the voltage. So it's saying that the amperage of that output is going to be 15 amps from the one string. If there were two strings, it wouldn't matter. And maybe let's just say you might want to extend that, so let's plan for two strings if you want to add panels in the future. Both of those are going to have a maximum output of 15. So what is the wire size that we need for that before it goes to your junction box? I'll just keep asking you, Fahim, since it's your system. So what do you
15
do? What do you do with that?
I times V, so 15 times the voltage, and the voltage would be,
Well, at this point, we're just trying to size the wire.
I see.
So I multiplied this 15 amp maximum output by
1.25.
1.25, which is the
And-
NEC safety margin.
And then the solar thing also, again,
Yeah.
with 1.25.
And normally with a string inverter, you would do that, but these power optimizers are located on each of the panels. So
Okay,
they're already mitigating the variability of solar.
I see.
So at this point, because there's an electronic device attached to each of the panels, we don't have to do that second 1.25.
Okay,
So what is 15 times 1.25?
18.75.
18.75. So if we look up at our table on page 104, you're going to find 20 or 12 gauge cable is more than enough to
Okay,
handle, the 20 amps going into that box. And typically the wire that you're going to be using is going to be 12 gauge that gets connected to the panels. So going into this junction box, 12 gauge cable, pretty straightforward. Now with a SolarEdge inverter, you're going to want to go from here, but we're not going to do a combiner box. We're going to do a junction box because each of these strings is controlled at the inverter. So we're going to be pulling basically 4 wires, 2 positives, 2 negatives through the conduit. And where is the next place we terminate in this solar design? What's the next piece of hardware we come to?
disconnect.
Yeah,
Box?
a DC
DC
disconnect.
Yes.
Now with the SolarEdge system, the DC disconnect is actually part of the inverter. So it comes all as one unit. So you'd actually come straight into the DC disconnect from the array, from the junction box, and it terminates into the inverter itself. Now, when we get together for our labs, you will actually do this. You'll connect into a SolarEdge inverter at the DC disconnect. Now, one of the rules about the DC disconnect is it's got to be within 10 feet of the inverter. Well, it certainly is. It's connected to it.
Okay.
Now, the inverter input circuit is already hardwired into this unit. So there's nothing you have to do to take the wires in from the DC disconnect to the inverter. So what is the output? Well, what's the output voltage coming out of this system? It's a grid-tied system, so it has to match your grid, right?
Right. So that would be 40 volts or
No, 240
240.
volts
okay.
AC, right? That's what you
Right.
get from the grid if you have single phase.
Right.
So what would be the ampacity coming from an 8 kW system? Well, power equation is watts equals amps times volts. So we would say it's 8,000 watts divided by 240 volts gives us how many amps?
33.33.
33 amps. Okay, so what do I do with that number to size the wire?
Okay. That will, I'd have to look up the table, right? Or
No, but it's
again.
times 1.25 because when we
Okay.
size the wire, we always put in the NEC safety margin.
I see.
So we're recalculating at this point. So we go 33
41 point-
times, what is it?
41.6.
2.6 amps. So if we look at the table, it seems to me 10 gauge wire goes up to 40 amps. So we'd probably have to go with 8 gauge wire. That's the next bigger size. I think that goes to 55 amps. So at this point, we're going to have to go with a number 8 AWG wire from the inverter.
Okay.
What's the next piece of equipment we go to?
AC disconnect.
That is correct. And that has to be located within 10 feet of the meter.
Yeah. So
Essentially.
it would be outside.
Yes. Mhm.
Right.
Now you could have this unit outside as well. If you lived
Right.
in California, that's probably where you would put it. But not all of us have sunny weather all the time. So in the Midwest, we're typically sticking this inside the house or the garage somewhere. And then we run to the outside. Now, what would be the ampacity rating of the AC box, the bus bar rating of the box? Well, AC disconnects usually come in 30 amp or 60 amp or 100 amp or 200 amp and so on. So would we use a 30 amp box or a 60 amp box?
60 amp.
Right. So we would use a 60 amp AC disconnect. And if we put a fuse in here, which I would recommend you do, get a fusible disconnect, what size fuse would we use?
40 or
You could use a 40 because we're in the safety margin here.
Yeah.
Although the inspector might require you round up to the next available from 41. So it might be a 45 amp break fuse. So that might work. I would feel comfortable with a 40, but the inspector might not. All right. Now from here, where do we go?
into the service, into the meter, or actually into the service panel.
Yeah,
So
into
back
our
in-
service panel. Now remember, the service panel has to be, you can't go more than 120% of the bus bar rating of the service panel. So this is going to your meter here. So let's assume if we have a 200 amp service panel with 200 amp service from the utility, then what is the maximum output we can, maximum input from the solar array that we can put into this service panel?
OT, so 120% rule. I'm
Yeah,
assuming.
so 40
that-
amps is the 120% rule. So we couldn't come in with more than a 40 amp breaker. Well, you're really only producing 33 amps.
Okay.
So you're still okay here. And that would kind of negate any reason for having a 45 amp fuse there. I'd probably want a 40 amp fuse in my AC disconnect at this point. So the wire size has to be at least 41.6. But because our actual maximum output is going to be about 33 amps,
Yeah.
we're still okay with a 40 amp breaker here. Once again, your inspector might become a stickler on that.
Okay.
And say, okay, well, you've got to round up 45 amps and now you can't put that in there. Well, that's problematic as far as the inspector. Now, if this box was not a 200 amp box, but a 225 amp box, which is another size that's fairly common, well, then we have no problem because the 120% rule is going to let us go all the way up to like a 65 amp service here. So 45 amp breaker, no problem. Another alternative we could do if the inspector gave us grief is maybe trade out this 200 amps main breaker for 190 amp. But you're so close, I just don't see that being an issue.
Okay.
Now this, if you did that, you'd have to hire an electrician to disconnect the meter and all of that, because you can't just trade out the main breaker yourself. But if assuming we can go in here with a 40 amp, you can just turn off your main breaker and you can make all these connections yourself
Yep.
as part of the design. All right. And that's pretty much your whole system. What size microinverter or what size inverter would you need here? Well, it's servicing an 8 kW system, but maybe, because of clipping, you might be,
7.6.
yeah, you might be able to go with a 7.6. Well, if you did that, then the output of this is designed to work with a 40 amp service. So then you're in no trouble at all. So, because the limitation is not going to be 33 amps coming out of here like we calculated. Seems to me its limit is 32 amps, and now it's 40 amp all the way. Which would then mean that you could go from an 8 gauge cable here if you wanted to a 10 gauge, save yourself a little bit of money. But these distances are not that great, so that part doesn't really matter that much.
Right.
All right. So it looks to me like if I were designing just for rough estimation for you, I would say if you want to put in SolarEdge, you could probably just go with their standard 7.6 kW SolarEdge inverter system. And that would meet the needs of your home pretty well.
Okay.
All right. Does anybody have any questions about what we've just done here? Have I confused the heck out of everybody? All right. I'm gonna let's see. Did anybody else who's on the call give me a power bill they wanted me to look at? Okay, that's easy. How far is anybody lagging behind? I haven't really done a check to make sure everybody's up to date. I figure you're all adults and you'll wait until the day before the labs and the tests to actually get through chapter 10 or 11. So really, I wanted to just take the opportunity rather than do the same problem we just did here. Anybody have any specific questions? Otherwise, I'll just call it a session.
So this is Albert. I didn't have a question per se, but the questions that are in the book, is there an answer guide to those?
Yeah, I can provide that, but also if you're using the online system to answer the questions, it gives you the answer right at the, as soon as you answer.
Right.
It will
There seem
give
to be
you
a lot more questions in the book though. Or is it the same?
than online. Huh.
Is it the same?
Yeah, they should be the same. Should be
Okay.
the same.
I feel like there are more labs online
Yes,
that
there
I
are.
couldn't find in the book when I was doing some calculations.
Yeah, there are more labs online. Just because, of course, there were some like how to use the NEC online tool or how to use PV watts, things like that you couldn't really do in the book. Some of the labs that are listed in the book, we will be doing in person. So we'll do some of those. But if you need the answer key, I'm happy to provide that to you. It's just I think the two should be harmonized. The online questions and the book should be. That doesn't mean, because when I did the last edition of the book, I did add some questions, and I may have screwed up in the online thing and not gotten everything matched up. So if you run into that, let me know so I can
All
fix
right,
that.
I'll look at it more closely.
Yeah, I should also point out that the questions in the book I feel are more difficult than the exam questions that you will face during the certification exam. Tried to make it a little bit harder than the questions you'll actually see.
Okay.
Jay, speaking of the,
Nope, go ahead.
when it comes to the exam, is it heavy on doing a lot of calculations?
No, I think there are 9 or 10 like math questions out of the 75. So normally when I have when I teach this at a community college or whatever, they're always scared to death about all the math questions. I mean, in theory, you could miss them all and still pass the exam. I hope that if you miss them all, you won't pass the exam, because that is an important aspect. Normally, when I teach at you guys' level, the math is pretty straightforward. I always joke that when I teach over at the University of Dayton and have graduate students, they're fine with all the math, but as soon as I let them touch the equipment, they set it on fire. You know, it's like they can't do the practical stuff to save their lives, but the community college students dress out all the cable properly. I usually take the labs from the Dayton graduate students and let the community college students fix them, because you know, things have been destroyed. So, but simple math questions you're going to run into, you will get a maximum and minimum string calculation that you'll have to do. You will get some sizing of the array, you know, based on, you know, what is the D rate, what is the insulation, what is the load need. You will get a battery sizing question. What else? Oh, voltage drop. I think.
Are they helpful and give you the equations, or should you try to commit those to memory?
No, the only equations that you have to memorize are watts equals amps times volts, power equation. The Ohm's law, you know, volts equals amps times resistance. And the voltage drop equation for sure, which is basically Ohm's law adjusted for distance. You know, volts equals amps times resistance times twice the distance divided by 1,000. Well, why do we do twice the distance divided by 1,000? Well, if it's 150 feet from point A to point B, there's actually 300 feet of wire, because it's a circuit, goes there and it comes back. So that's 300 feet of wire. And the resistance that the NEC gives you is in resistance per 1,000 feet. So you're just adjusting the resistance based on what are the actual measurement of the wire distance, not their standard that they've given you, which is per 1,000 feet. So that's the voltage drop equation. Very simple to remember if you understand it's just Ohm's law adjusted for distance. And then there is one other thing that you need to sort of remember when you're doing the string calculations. A ground mounted system for the minimum string length, ground mounted, you add 25 degrees. Flush to roof, or a roof mounted ballasted system, you add 30 degrees, and a flush to roof, you add 35. So that's, you know, with the maximum, you just take the coldest temperature that has ever been experienced on the site. But for the minimum, you take the hottest temperature. And then because it's hotter on a roof than it is just ambient air temperature, you add in 25 degrees for the ground mounted, 30 degrees for a ballasted system, 35 degrees for a flush to roof. Now, the question is going to say, you know, what is the minimum string calculation, assuming this is a ground mounted system, or assuming this is a flush to roof system or something like that. So you'll have all the information you need. There are no tables you have to memorize. You don't have to memorize the ampacity table or anything like that. Any of that information, they're going to give it to you that you need to know. But those equations, you're going to have to remember. Now, the other thing that's tricky in here, they're not designed to be tricky, but it's just the reality. You'll have a lot more information than you need to figure these things out. So it's going to tell you a lot of information that you don't care about. You have to know what's relevant to calculate this and what's not relevant. And that's what trips up a lot of folks. You know, so many students get used to the fact that I've been given 3 numbers and I'll just keep plugging these numbers in until I get something that is an answer that I can pick from the answer choices. You know, that's kind of, I mean, we've all been students. We know that's the way you do it, you know, just play around with numbers till something comes out. I will tell you, the questions are written that if you use the wrong numbers, one of those answers is going to match those wrong numbers. So you can't just do it that way. You can't just arbitrarily play with numbers till you get something that works. So you will need to understand it. That's the goal anyway.
Could I ask? Sorry, I'm on spring break right now, and I normally have class during this, so I've never been able to come before. But
Sure.
I was, and if you've already kind of gone over it, that's totally fine, and I'll just stick around for the end of class. Is it all multiple choice? Or are there like short answer sections? What is kind of the format of the actual test?
Yeah, the test itself is 75 multiple choice questions. So there are 4 answers, of which you will choose one. There is a correct answer. Some of them may seem sort of correct, but there is a real correct answer.
Okay.
If you don't answer the question, you get it wrong. If you answer the question wrong, you get it wrong. So there's no penalty for guessing. So make sure you've answered every single question. You need a 75% in order to pass the certification. So that means you could miss 18 questions out of the 75. And since there are 9 or 10 math questions, you know, in theory, you could miss all of them. And but don't do that.
I'll do my best not to. Yeah.
Yeah, I mean, you guys are all pretty good at math. Otherwise, you wouldn't be where you're at. And this is not calculus or trigonometry or anything. It's just multiplication, division, subtraction. When we get together, you can use your own calculator if you want for the test. I'll have calculators, just little simple ones that cost me $1 at Dollar General. You can't use your phone as your calculator because your phone has other things you can use it for. So we don't allow that. But you'll have 2 hours to take the exam. That's more than enough time for most folks. If you've got a disability of any sort, let me know ahead of time. I can extend that time period. You know, if there's a reason for that, you know, it could be visual, it could be comprehending questions or whatever, or you just need more time for whatever reason. You know, again, we're pretty mellow about that as well. But most of the students will get done within an hour. You know, you've got 2, so that's all. It's pretty straightforward. It's an entry-level certification, not designed to be super, super hard. If you've gone through, if you could answer all the questions at the end of the chapters, you should do just fine on the test. Obviously, there's 250 some questions, I think, in the course. There are only 75 in the exam. So you're getting a lot broader knowledge base from the course. So
Awesome. Thank you so much.
sure thing. Where are you on break? In Tahiti?
That would be better. I'm in did a little road trip to Louisville and Nashville.
Oh, okay. All right. All right. It's not on the beach.
It is not. It was supposed to. The
unfortunate.
idea was that it was going to be a warm little like, oh, go down to the south, and of course it was like snowing in Nashville. But
Yeah. Mhm.
Yeah.
All right. All right. Anybody else have any other questions?
Hey, Jay, this is a random question. So I ran across a vendor, GAF Solar. They're a roofing company, and so they just actually incorporated solar cells into the roof.
Yeah.
What do you think?
I don't like them. Yeah, I mean, we run across solar shingles, you know, periodically. GAF is definitely the biggest currently. Tesla tried a whole solar roof thing or solar shingle thing. It was all hype and no performance really. GAF, the thing I always come back to is what is the problem it's trying to address? You know, why am I worried about solar shingles? Why would I choose that option versus just a regular rooftop mounted solar array? Almost always it comes down to aesthetics. I don't like the way it looks. Therefore, I want something that kind of disappears into the roof. Well, there are some other options that are out there. But the problem with solar shingles is if one of your modules fails, then you've got quite a project to, you know, you got to rip up portions of the roof if and fix it. I think the GAF system, the wire management, has been addressed by having raised channels that go along the side of the shingles. Well, visually, you can tell they're solar. You can tell they're solar, it's a solar array. It's
Right,
not
right.
just invisible shingles. So it looks like a problem in search of a solution, or a solution in search of a problem, I should say. I personally don't think aesthetics of solar is that bad. And if you do, well, you can come up with ways of hiding those solar panels, like building yourself a solar pergola, in the backyard, or they do have a film that you can adhere over top of the solar panels, sort of like you see those advertisements on buses that on all the windows. Well, this is something that they call them like solar skins, where you could get a skin that matches the appearance of your roof and adhere that to the panel, and sort of make it disappear. Doesn't totally disappear, but it's as good a disappearing act as a solar shingle. But I just come to terms with the fact that you've got solar. It's like
Yeah.
that they make some very attractive now flat black solar. So it really is just a clean black. And they're getting some, like I saw a webinar, I heard a webinar from Toledo Solar, that they're into the thin film solar panels, and their panels are glass encapsulated, but they're only about 3 millimeters thick, as opposed to the normal 45 millimeters or so of a solar panel. So it's like the thickness of your cell phone. And so they're very low profile, very sleek looking. So you could put a solar array up there that would be jet black, very low profile, very sleek, and look pretty good. So, but I guess I don't like them. They cause more problems than they're worth.
They didn't seem as efficient either because they projected a lot more panels.
Yeah. They're not. They're a thin film. The other issue with that is you're putting them directly on your roof, and these solar panels need air cooling, passive cooling. So that tends to cause them to degrade a little faster. I mean, GAF is they're a roofing company, so they're just trying another product, but their main business is roofing, not solar.
Okay, thanks.
Sure. Philip?
Hey, Jay, I got a question. This is totally off the wall question, but we talked about, you talk about shading. How about reflection? Is I don't know if reflection can give heat or give any type of energy to a solar panel. Not a scientist. I'm just here taking this class, and
Sure.
I'm learning a lot. So, and I just didn't know, I just thought about it the other day. I was like, oh man, it's reflection. I was like, well, if it's shading, is going to hurt the solar panel. Can reflection help the solar panel?
Yes. Yes. The answer is yes. And so your logic is there. In fact, I was just doing a solar assessment up at a fish hatchery, and they have a whole bunch of ponds, and it turns out where they wanted to install the solar array is on the north side of one of the ponds. And so we're talking about, if we increase the angle slightly, will we get better reflectivity off the water and increase the harvest of power, because it's coming from the south, hitting the pond and then bouncing up. Another thing to consider is, would you want to put bifacial solar panels, where now you're absorbing from underneath the panel as well as from on top? Those are oftentimes used in areas like if you're putting a solar array out in a sand environment or a snow environment. You would use bifacial panels because now you're getting the reflectivity off the ground and it's bouncing up and being harvested underneath on the bottom part of the panel as well as on the top. And the studies will show that the cost versus benefit is often in the favor. You know, the bifacial might cost you 10% more for the panel, but you'll harvest 15% more power. You know, that kind of thing. What you're really thinking about is if you think about concentrated solar, you know, if you can take a greater proportion of sunlight and concentrate it onto the surface of the panel, you're going to get more energy. So reflected off the ground, reflected off, you know, the clouds, reflected off snow, reflected off almost anything, is going to give you additional power.
Well, because what I guess what you answered the question and everything perfect. I was just trying to maybe we invent something like, you know, your solar panels this way and it's looking towards the and then the sun, and then when the sun goes over the solar panel, is there any way to counteract that reflection off the sun to hit the solar panel so you get maybe more daylight or more energy, I guess.
Sure.
I guess maybe that's a little engineering stuff that could happen, but it's probably not efficient.
Well, I've heard of, you know, kind of in a different vein, but it could be used for solar. You know, if you're in a valley environment, a mountain valley environment, there are some cities like in Sweden was the one I was looking at, where they actually set up reflective mirrors up on the mountaintop to reflect sunlight down into the city square, so that in the wintertime, people come out and sunbathe in this intense light, you know, right there in the city square, where you could do that, you know, reflect light to your solar panels. Probably it's going to be more expensive than if you just simply put in a couple more panels. But, you know, there's always people coming up with these ideas. They've talked about space-based solar and taking solar concentrators in space and then aiming them towards a receiver, you know, to concentrate the sunlight. Those I, again, tend to dismiss because I can't see that as anything but a weapon. You know, it is basically almost a low-end laser beam. And it's always being proposed by the military. So that makes me a little bit, you know, their argument is, okay, we've got troop movement going and our convoy is moving from place A to place B. Wouldn't it be great if we could then direct our solar receivers, you know, to receive this energy, you know, in a mobile form? And you go, yeah, you know, I could see that, except really what your weapon, you're making a weapon, you know, I mean, don't pretend it's not. And, you know, so, I mean, if you, even if you talk about like a, what did we call those? Fresnel lenses, the ones they have in lighthouses, but they're these concentrator lenses, and you could get them from the old big screen televisions. And we had an intern who harvested one out of a big screen television and set it on the porch. We have a wooden deck, and forgot about it. Well, as the sun tracked across the sky, it basically burned a streak across the wooden porch, the wooden deck, as this concentrated solar just, you know, engraved its little mark across. So anyway, there's lots of options there. And I think if you want to invent something, the thing I would invent is, how can you charge electric vehicles for people who live in apartment buildings or have to park on the curbside? You know, that's an issue. That's a big issue.
Well, I was thinking about that as well after I had a horrible basketball weekend. Like those carports and everything like that, as you know, carports and stuff like that. I don't know. I guess there's a lot of shade. Well, I guess with the trees, anywhere you go, you just got to watch out for the trees. But a lot of those put together in one day carports and stuff like that. Maybe somebody can invent something like that where because carports are just coming up everywhere
Sure.
because they're cheap. They're sturdy, but they're also cheap. And I don't think you get taxed on them. So just maybe some of those roof, maybe you guys talked about shingles, solar shingles, but I mean, you can also, those are the probably the tube steel and everything that the solar panels go on. Those are already made right there. So just throw some solar panels on top of that.
Yeah, they do have solar carports. And in fact, we're going to be installing one here at our office. So that is a thing for sure. And there's like Blinker, I think, is a company that makes them, but you can just use a regular ground mounted system and raise it up off the ground as a carport. And we've done that before. That's very common. But what I was thinking is, if you don't own a parking space, it's not yours permanently. How are you going to charge your vehicle if you're in an urban setting having to park on the street, or in an apartment area that doesn't have reserved parking? What we need is some sort of portable charging station. And I can think of a million reasons why it will never work, but maybe if somebody could invent it, there's a big market for it, so that will be something other than dragging a cord across the sidewalk and laying it in the gutter. That would not be the best mechanism. All right, well, we've come to the end of the hour, so we'll see you guys all next week. And in the meantime, if you have a question through the week, just drop me an email or give me a call, and we'll try and get you there. But next week will be our final session. Then we start going into the labs. A week from this upcoming weekend, I think we're going to be at Oberlin, if I remember that sequence right. Then I think we end up maybe in Indiana, and then at Hiram. I think that's the sequence. So anyway, that's it. We'll see you next week. All right, take care.
Thank you.